Okay, so hi everyone, welcome to today's data learning seminar. So we are very glad to have today Didier Lucor, a senior CNRS researcher at Paris-Saclay University, and he will talk about coupling of deep neural networks and physical invariants for turbulent flow surrogate modeling. So Didier, I will leave the audience with you.
Okay, thank you, Sibo, for the introduction, and thank you for the invitation today. So I'm Didier Lucor. I'm part of the LISTEN lab. So it's interdisciplinary laboratory of numerical sciences. So it's a lab that is very recent, actually, because it started in January 1st, 2021. And it was actually because of the merging of two different computer science labs. So now in Paris-Saclay, there is only one, much larger. And it's kind of a very interesting and motivated to work here. Today, I'm going to present some work I've been doing with one of my colleagues in the lab, Anne Sergent. She's a little bit the person who is an expert in producing this type of simulations that you see here in the image. And this work was also performed by two master students that we have co-supervised recently. And today, basically, I'm interested in trying to use and adapt some machine learning techniques to this physics here that usually we solve with direct numerical simulation, something we call DNS, which are very, very large simulations. So I'm going to give just a little bit of context. We're interested by this natural convection. So the natural convection is something that is going to originate quite spontaneously in the fluid at rest. What you do is actually you impose a temperature gradient to the domain. For example, you have this hot plate here at the bottom, and then you have the cold plate at the top. And this temperature gradient is going to, through some diffusion process, is going to bring actually some change of temperature in the fluid bulk. And this, for some regimes, is going to, through an instability, this is going to trigger a fluid motion, which is in turn going to affect the heat transfer through the bulk, okay? And what you get, so here the type of flow we're looking at is very, in a sense, canonical of this type of heat transfer application. It's called the Rayleigh-Bénard cavity. And what you get is this very complex flow that looks a little bit like a very large structure in space, a little bit like a washing machine spinning. And then on top of this, you have much smaller flow structures. They are called the plumes. They look a little bit like filaments or mushrooms. And basically, those very small scale plumes are believed to be the primary heat carriers. So it's important to resolve them and understand a little bit how they behave in relation to the mean flow, okay? So the important parameters for this type of flows, you have the Rayleigh number. The Rayleigh number is some kind of ratio between a typical time scale for diffusive thermal transport and a time scale for convective thermal transport. And this non-dimensional parameter relates to the Nusselt number, which is a measure, let's say, of the global heat transfer through the cavity between the top and bottom walls. And if you do experiments and you collect all the data in this plot here on the top right of the slide, you can actually find a relation between the Rayleigh number and the Nusselt number. And all the curves, they nicely collapse with this in this power law of exponent 1/3. But then eventually, if you have a Rayleigh that is large enough, you get a strong departure from this power law, and you get something which follows an exponent with a beta of half, let's say. And this is a signature of what is called the ultimate heat transfer regime, where you have much stronger heat transfer. And people want to actually understand and trigger a little bit this instability. So the problem is to get that, you need a very high Rayleigh number. The flow is very turbulent in this case, and this is very expensive numerically. So one way to promote actually this switch, for example, you can use roughness. You can add some roughness at the walls. For example, here you can guess you have some roughnesses here on the left. I don't know if you see my mouse. I hope you do. So adding those roughnesses is going to help, you know, modifying the boundary layer and modifying the thermal transition. This is going to kind of trigger this instability even for lower Rayleigh number, which is a good news for us. So the equations we're solving, okay, later on I'm going to use machine learning, but I'm going to rely a little bit on the physics. So I want to use those equations. The equations we're solving, if we perform DNS, we have Navier-Stokes with the incompressibility condition here, equation 5, and then you have conservation of momentum, the equations 2 to 4. And then you are under Boussinesq approximation, which means that you assume that the fluid density variations are reasonable. So you can just add this forcing term to the momentum equation. You have a forcing term that is proportional to the temperature and is acting as a buoyancy term along the vertical direction, okay? And then, of course, you have the advection and the diffusion of the temperature field. And you can see that later on you will understand that we are curious about the type of information and the type of data that you need to have to kind of solve the system without having too much data and without having necessarily data about all the fields. Maybe you have only data about temperature, but still you want to infer and you want to, in a sense, reconstruct the velocity field. Okay? So in the top equation, you see that you better consider a region of the domain where you have temperature gradients, because otherwise the second term, the coupling here between the gradient of the temperature and the velocity is not going to be, you know, affected in a sense. And so there is a very big discussion, and it's important to consider what type of data you have, in what amount, and where in the computational domain. Okay, so when you do direct numerical simulation, when we do that with the in-house solver, the finite volume solver, it's like super expensive. The CPU time is very large, but especially if you want to save the solution. So the time step for the DNS is very small. It's like 10 to the minus 5. And every time step you would have to save about 33 gigabytes of data. So in fact, DNS is very expensive, but you cannot even save it. You cannot store it somewhere and study it later and kind of go through all the data as you would like, okay? So it's not easily portable. And in fact, it's kind of a waste. You compute a lot of things, but that goes to the trash in a sense. So you're saving the solution maybe in some slices along like 2D slices, or maybe you're saving a 3D field, but not very often, something like this. Okay. So we are also collaborating with some people doing experiments. They have very sophisticated experiments, as you see here on the right-hand side. Here we're looking at shadow graphs. So what they do, they use a cavity that is actually transparent and with a very strong light, right? Basically, because of this transparent media, the turbulent structure are going to refract the light rays, so they can cast some shadows. Okay, so what you see here is it's like some kind of 2D projection of the three-dimensional flow. So you see many different structures. I hope you see the animation. It's a movie, so you can see the plumes. But what you see is actually just a projection of the 3D flow. So depending if you work with DNS or if you work with experiments, both of them, they are kind of interesting for some aspects. For example, in space, for the DNS, you are very well resolved, but you cannot really perform very long simulations, right? You cannot change the parameters too much because one simulation is already very long. But you have access to all the state variables, temperature, pressure, anything you want. For the experiment, you can run it for very long. Either you have a partial representation in space, for example, here we have the entire cavity, but it's projected, or maybe you have PIV somewhere, not everywhere in the domain. You can change the parameters very easily, the setup of the experiments, but you don't have access to all state variables. For example, this is what you see here is some kind of Lagrangian form of the temperature field. So you don't have information about velocity or pressure. Okay. So it would be nice to be able to have machine learning techniques to kind of take advantage of both numerical and numerical experiments and experiments performed in the lab. So when you look at the literature a little bit, people using machine learnings for turbulent convection, very often they use supervised learning. Very often they use CNN. And what they do is try to actually detect some patterns, detect some correlations between various turbulence quantities, for example, such as the heat transfer. Okay. But at the end of the day, very often they look at 2D things. And in any case, they strongly rely on DNS. I haven't found much experimental actually work using machine learning. So I have two research paths a little bit to present. I will spend most of that time on the number one, which is physics aware of physics informed DNN to be able to actually reconstruct, in a sense, the DNS. Or we have also some results where we are trying to use CNN this time, apply it to shadow graph image, and trying to basically extract some heat transfer scalar, a Nusselt number that is a measure of the 3D heat transfer. So from a 2D image, that is this projection I was showing, can you provide an image and can you recover the 3D heat transfer through the entire cavity? Okay, so for the first part, I will, and in the following, we look at basically two types of flows. The first one, the Rayleigh number is quite low. So it is mildly turbulent. It's the movie you see in the top right. So we're looking at some isosurfaces of temperature. And in this case, we will have some roughnesses at the bottom. So you cannot really see them, but you have two of them, two little cubes here. The reason why we do that is actually to focus the flow at this location, to have the plumes kind of aggregate at this particular location. So when we reconstruct, actually when we do the modeling, we know that the plumes are going to go through our domain, right? The other case is much more turbulent. The Rayleigh number is 210 to the power 9. You see that, and it's smooth. Okay, so it's a more challenging case. The structures, they go a little bit everywhere. So even if we kind of focus on a particular subdomain, it's much less regular. We are not guaranteed that the structures, for example, are going to be advected from bottom to top. They might enter from the side. So it makes the learning much more difficult. Okay, so this is just the movie you see at the bottom right. This is just a 2D slice of the 3D flow. Okay, so it is a 3D flow, it's just represented differently. And of course, if you monitor the spectrum for example, of the temperature or the velocity somewhere in the domain, you get this turbulence kinetic decreasing the growth. The spectrum is shows that it is indeed a turbulent flow. Okay, so we're going to use a technique called PIN. So I don't know if you are familiar with this. It's PIN stands for Physics Informed Neural Networks. So the idea is to use some data. So we're going to use some data from the DNS. So after running the DNS and having access to everything, we're going to select a little bit of data from the DNS, give that to the machine learning techniques, but to make it more efficient, to make sure that the training is efficient and the machine learning trains quite quickly, we're going to add some physics, and I will explain how. And through this physics, we're going to be able to recover hidden variables. So the data will not necessarily be collected for all fields, but still we'll be able to recover, to reconstruct pressure, temperature, and velocity fields, okay? That will provide a strong data compression. So far, what we're able to do is we're able to do it with good accuracy in a small portion of the entire box. So what you see in black here on top of the roughness, this is in this subdomain that we're going to reconstruct the solution using small data amount, right? Kind of scattered data amount. We're going to reconstruct the solution both in space and time at the same level of accuracy as the DNS. Okay, so the way to do that is to rely on this PIN machinery. So I don't have time to enter in great details, but essentially you have a deep neural network here at the front, represented in blue. So the inputs in this case are really the same, let's say, free variables that you have in your PDEs, in your equations. So the inputs are space and time. So if you are in 2D, for example, you have X, Y, and T. And then you're going to predict the solution. So here I have written only temperature and pressure just to make it smaller. But you predict all the fields. And what you do is you actually add something represented here in green. You're going to add some constraint. So you're going to actually try to enforce in a soft manner, in a sense, you're going to enforce the PDEs, okay? So you're going to enforce the equations that you know them, the equations of the system I've presented at the beginning. And the way to do that is actually to add this penalty term to the loss function. So the loss function contains the usual difference term between the solution produced by the network and the data, okay? So you're going to take this average expectation of this quantity, which is basically how good you predict the data. So here, my data are written U underscore. What my point is that the data, for example, can be only about temperature, nothing about pressure, okay? Just relative to one of the fields of the system. But then you have this additional term, and this additional term is basically the residual of the set of equations, okay? So if you have a way to evaluate the equations at particular points in the domain, okay, you compute the residuals. If you do a good job, then the residuals are very small. So minimizing actually this quantity normally ensures that you satisfy the equation and that therefore you're going to recover the right solution, okay? And to do that, of course, you need to evaluate the equations I was showing before, those equations. So you need to evaluate spatial and temporal gradients. And in order to do that, you rely on this very nice automatic differentiation. So it's very easy actually with all these libraries such as TensorFlows and PyTorch, and to actually get to differentiate basically your outputs relative to the inputs. This is something that you get right away. So you can indeed evaluate the residuals. This additional term is going to regularize, is going to guide the learning, and is also going to, in a sense, help in doing a good job, even if you have small training data. Okay. And also the second benefit is that you're going to recover hidden variables, for example, the pressure, even if you don't have any data about the pressure. But then, of course, there are some open issues about where do you, so which data field do you collect, at where in the domain? What about the training domain? How do you choose it? What about the data set training size? You have all these choices that we have tried to actually study and try to get some experience about those choices. Okay. So the first case we have here, we construct a pin architecture. So we have 10 layers. Here we are in 3D, so the inputs are space and time. We have 300 neurons per layer, so it's quite a large network. And then we are using the very standard Adam stochastic gradient descent algorithm. And we have some tuning, a little bit of hyperparameters. We're doing this with TensorFlow. So basically, this is quite nothing special about that. But then it's a little bit more important how you actually collect your data and how you construct your database. So as I said, you cannot save the DNS. It's too big. So from the DNS, you make a choice of the resolution in space and in time of the database you're going to construct. Okay, so we have two sets, more or less, three sets. One is for small Rayleigh number, the other one is for large Rayleigh number. Okay, and you see that in this black box where we are trying to reconstruct the solution, for example, we choose a spatial resolution 26 by 26 by 38. So we have a quite refined grid in this box. And then in time, we have 100 snapshots, for example. So the total amount of data with this resolution amounts about 2 million points. Okay, so here I'm talking about points in space and time. Okay, and then you can play with the temporal sampling. You can play with the resolution. You kind of make the data set smaller to see the impact on the results. Okay. The database for the large Rayleigh number is much bigger. It's more refined in space, and in time also you see the time step is a little bit smaller. So you build your databases, and then from those databases you're going to feed actually your pin models. So again, you have some choices to make about the size of the training data set and the size of the testing data set, because you're training on the data set and then you're kind of testing on a different one to be fair and to be sure that you generalize well. Okay. So we have different models here. I have presented a few of them. Essentially, I have the bold one is called the reference one. So you see in my first database, I have 2.5 million something data points. I'm going to use 2 million data points, and I'm going to test on the remaining 500 something data points. So I make a choice of using a lot of data. Okay, and then I will lower this amount of data, and we will see, what is, how the results come out and what we propose to improve that. So I'm not sure I have questions. Actually, I don't see that. interrupt if you have some questions. So here we have results for the case where I have a lot of data. Okay, here you see the decay of the loss function, and here you see some accuracy metrics in terms of the root mean square, or for example, the error in the mean, the error in the standard deviation. Here, the error in the statistics are in percent. Okay, so when I have 0.4, it's 0.4% error on the standard deviation of the temperature field. So basically, I have very accurate results. It works very well. And I forgot to mention that when I construct my database here, what I use in the subdomain, it's data from the temperature field. So inside the box, I collect temperature points, okay? But then for the velocity fields, I'm providing velocity information only on the box faces. So I'm only providing velocity information for the side faces and the side at the bottom, not the side at the top, not the face at the top. Okay, so I'm providing velocity at the boundaries of this domain in subdomain in black. Okay, so I'm providing very little velocity information and only temperature data points inside. Nevertheless, I'm able to reconstruct the entire velocity fields inside the domain. Those are average accuracy metrics, okay, average in space and time. Okay, so it's a summary of the accuracy I get for the temperature, for the velocity, for the pressure. So I get very good results in this case, okay? But I get good results, but I have a lot of data. So another way to monitor the accuracy is actually do this scatter plots here. So I'm putting all the data points I have tested. Okay, so all the data points I'm trying to reconstruct in this subdomain with the machine learning against the reference, against the DNS. Okay, so if everything is aligned along this 45 degrees angle line, so I'm very accurate. So all the data points here are in space and time all together. Okay. So I do extremely well for the Vx component of velocity, and I'm doing well, but not as well for the pressure. And this is something very consistent. The pressure term is more difficult to capture because I'm not providing any information about the pressure at all. When I divide the amount of data by 2, so the 1C7 model, I have half the data, so I have much less data. Then in this case, I'm starting to lose the accuracy, especially for the pressure. I'm not doing as good as before. Okay, so when I'm in this small data regime, it doesn't work very well. Okay, and turns out that if you look at a little bit more closely in the domain, you know, do you get uniform error? What about time? Because you train actually your model within a certain time window. So is it kind of uniform, the error in time? Is it uniform in space? It turns out actually that the generalization error that you get is not uniform in space or in time. Actually, you get lower accuracy in regions close to the boundaries of the training domain. So in space, for example, you would be, with your machine learning reconstruction, you will be a little bit less accurate close to the boundaries of the black box here. And the same in time. So here we're looking at the L2 error of the pressure in time. Actually, the error is larger at the close to the initial time and just before the final time. So close to the spatial and temporal boundaries, the error is larger, okay? So especially when you are in this small data regime. So an idea we had was to use what we call penalty padding. So here I'm representing a a domain, okay, very kind of cartoon representation of this domain, both in space and time. So here I'm considering only one dimension in space, okay? So let's say X, and vertical direction is time. We're trying to reconstruct our solution, our flow fields within the gray box, okay? And inside this gray box, we have data points where we collect data, and we have what I call residual points where we are trying to make the residual of the equation small. So the first thing is, because of the stochastic gradient descent, the way you're going to sample the points is random. So you have your big basket of data and you sample, you have this mini batch approach where you're going to sample a handful of data, and the location at which you collect the data is not the same than the location at which you minimize the residual. The points are not collocated, okay? They might be, statistically they might be, but there is very little change. So when you do the approach the standard way, the accuracy in the hatched region here is poor, okay? So what we decide to do is we keep the same budget. So we keep the same numbers of dots and the same number of stars. So if we have 1,000 data points, we have also 1,000 points at which we impose, at which we minimize the residual, right? So number of dots and number of stars are the same. But what we do is we pad actually the region. So around the region of interest, we pad with additional elements where we actually place residual points. So what we do is, around the black box, for example, we do some padding in space. So you see you have some extrusion here in white or in light blue. So you can have extrusion in space, okay? But you can have also extrusion in time. And in those, surrounding regions, you're going to minimize the residuals as well. You're going to minimize the equations that you know, okay, in the same way you were doing before. It's just that the density of the stars is lower within the gray domain. And by doing that, you actually regularize the outside, and this helps a lot improving the accuracy in the hatched region where you had poor accuracy. So, not going to go too long on this, but the middle line here, the results were the bad results from before. And when you do the padding with the same computational budget, just a different way actually to positioning your residual points, you get back to the original accuracy. So even with small data, just using the padding, you do as good as with the big data you had at the beginning. So that was one strategy actually to improve a little bit the predictive accuracy of this spin model. Another thing that we have tried is actually, when we move to more turbulent case, so when we move to that case here at the bottom right, the scales are smaller, everything is more difficult. So even if we pick a particular subdomain and we're trying to set up the methodology, we need too much data or it doesn't work very well. So what we've tried to do is to look at the convergence of the different terms. Okay, so this is our loss functions, but the loss function, you can look at the loss coming from the data. You can look at the loss coming from each of the PDE. You can go inside the formulation for the pins. So you can go inside those blue and green terms and look at the convergence of those, but kind of separate the effect of the green contribution, because within the green contribution here, you have all the PDEs. So you have 5 PDEs for the temperature, for the velocity fields, for the divergence free, okay? And you can monitor those And you can see a little bit if there is an equation that is more difficult to enforce, that the optimization algorithm in this kind of new loss landscape had some problem minimizing. And the equation is struggling with is actually the incompressibility condition. So the incompressibility condition is trying to make it divergence free. And it is represented here in yellow. And as you do your different epochs and your learning cycles, it's kind of decreasing, but kind of piecewise decreasing. It does not really decrease smoothly. And you see also that the data contribution, so the data is actually the label here in the cyan color, is kind of stagnating. So the results here in the A case on the left are not very good. So what we propose is actually to relax a little bit the surrogate constraint. So if I represent a little bit the loss function here as some contributions, the data, the labels being broken down in the bulk, the boundaries, the initial conditions. So this is fine. People have proposed some weighting of those quantities, adaptive weighting of those terms on the label side. This is one approach. What we do is actually to look at the PDE side, and we assign some weight to each contribution. And what we do is that we carefully tune the weight to kind of relax actually the last equation here, the PDE5, the one related to the divergence. And this actually helps tremendously. So just changing the weight of this contribution not only is going to reduce a lot the error of this particular equation, but it's also going to benefit all the other constraints. And it's also going to benefit the terms associated with the labels. So this is amazing. It's really a coupling in the loss between the minimization of the term with the data and the one with the PDEs. And by relaxing here some of the PDEs, you can also lower the loss function for the label. And when you do this, you go from, for example, just relaxing as I proposed, you go from results here for the scatter plots where you have those gray cloud here that is not good at all. You go to the red. So everything becomes much more precise. You reconstruct the solution very well. And even if you look at some probability density function for the temperature field, people actually expert in the natural convection, they know this PDF where you have this long tail here on the right. And when you perform the relaxed pin version, you really capture the long leg effects here in the PDF. If you look at some plumes, so here we are using the pin surrogate model to predict a particular solution. So here we say predict the solution at a particular time. So the top line here, you have the vertical component of velocity, and here you have temperature at the bottom. You see this kind of plume here that is very elongated, very strongly anisotropic. When you have the relaxed version of the pin, you capture all the scales. If you have the standard approach with the same amount of data, everything the same, you don't capture the small scales. So we were very pleased actually with those results. Okay. Yeah, I won't have time to talk about the other part. So I'm just going to recap a little bit. What we have tried is to find a way to actually reconstruct a DNS solution of a turbulent flow that is too expensive even to store or too expensive to explore. So we would like to have, a more agile, a more flexible, reduced order model to kind of replay those data and maybe do some post-processing or something like this. So to do that, we start from some data from the DNS, and we're trying to reconstruct actually the solution with the same accuracy as the DNS, but using as little data as possible. Okay, and what we want to do is to get this generalization error on all variables, including hidden variables, below a few percent. And we thought that the PIN formulation was nice because it's very versatile. You can add very easily any constraints that you want. You can play with the formulation. It's very easy with this automatic differentiation to evaluate actually the residuals. But we thought it would be nice actually to kind of decouple a little bit the data points from the residual points. Also investigate some padding techniques, a little bit inspired from this immersed boundary approach that we have, something where we want to impose, for example, a rigid body somewhere in the floor, something like this. So we got good results doing this, but the best results we had actually was to relax actually the PDE related to the incompressibility of the flow. That helps really, you know, the optimization, and we were able to reconstruct actually very strongly turbulent quantity inside the domain. Yeah, so I will have to pass on the CNN part. If you have some questions, I can go back. So my message is that I think it's quite promising, at least for turbulent people. We have seen machine learning apply to all this kind of hierarchy of approach, from parameter to closure term estimation, for example, people doing RANS or LES. But even now we might consider even using that for full PDE modeling. There is a lot of work to be done, in particular for the generalization. All the results I've shown, I'm training within a domain in space and time, and then I'm reconstructing or I'm interrogating the surrogate model within the same domain. I'm not extrapolating outside. I'm not asking the PIN model to predict for later time or something like this. And I think also the thing to do next is actually to do the same, but with experimental databases. So the data are going to be noisy, incomplete. Can we do the same with experimental data, enforcing in the same way the PDEs that we know? But that will also bring the question of how do you validate results? How do you check that when you test your model, you recover what you are supposed to get? Because usually from experiments, you don't have, you know, everything. So it's kind of hard to perform the validation step. Yeah, so I'm going to stop here. I just have the paper that basically explains what I presented. If you want to look at it, the archive version. Okay, so I don't hear you.
Thank you a lot, Didier, for the nice presentation. So if anyone has a question, so you can either unmute yourself and ask the question, or you can also leave the message in the chat so I can read the question for you. So meanwhile, I have actually a couple of questions. So first, if I understand well, I think you're trying to predict these physical fields in a subdomain, because the large physical fields maybe is too large, you have too many outputs to do that directly. So I was wondering, do you think that would be possible, for example, if you can do some reduced order modeling so that you can reperform what you have done here, but in some reduced space, so that you can directly provide this prediction in the whole space? I don't know if you have any thinking about that.
So you're saying, you're saying you train in the small subdomain, but you predict outside to see what you get?
I'm saying, for example, if we can do something like the POD, for example, to reduce the dimension of the space.
Yeah, so the POD is a little bit different because it's unsupervised, right?
Yes.
So here it is supervised in the sense that I'm the one, controlling the network. I say, okay, I use 10 layers. I'm deciding on the activation function. I'm deciding about everything. I'm not doing some kind of auto encoding or POD to extract some modes. This is not the approach that I'm using.
Okay, thank you. And I see there's a hands up.
So I mean, of course, what you're saying is relevant, but it's completely a different approach. Here, it's more like, it's almost like my machine learning technique is going to be some kind of PDE solver, because my inputs are really the coordinates you see of the PDE, and the solution are just the fields that depend on these coordinates.
Yeah, I see. So that you can have the exact solution. So with the PDE in the full space, it's not like in the POD, you may lose some information, right, when you reduce that.
So here you may lose some information because your modeling architecture is not, powerful enough or something like this. For example, if you're not careful here, you see you have a big difference between the reference here on the left and your prediction. You don't capture all the scales. So if you just compare the first column with the last one.
Okay. So so exactly in this case, we can see some difference between the prediction.
So here you have some difference because I'm trying to reconstruct. First of all, I'm reconstructing the solution at a particular time step that was not in the training time steps, you see? So I have some snapshots in time, and I'm not asking to predict exactly at a particular snapshot that I was using for training. Otherwise, it's too easy, right? So I'm kind of asking to predict the solution in between two snapshots. So that's the first difficulty. And the second difficulty is that to be able to reconstruct all of this, I provide the machine learning with not that many data. And also data about temperature, not about velocity, for example.
Okay, I see. Thank you, Didier, for the answer. So I see Rosella has a hands up. So please unmute yourself for the question.
Yeah, so first of all, thank you very much for the talk. Very interesting, brilliant. Thank you. So my question, I have a couple of questions. My main question is more about the model that you are training with the PDE. So in terms of efficiency, or let's say execution time for the training, especially for the training part, do you have any idea? Because I didn't see any results in terms of comparison between the execution time for training this kind of model with respect to a standard data-driven model. But I was wondering, so how much do you think the presence of the PDE in the training process will affect the time complexity and then the execution time?
Yeah, so from what so if I understand your question, you're asking, okay, do you see the slide here again?
I see that.
Yeah, okay. Yeah. So you're saying, well, now you have this green part, right? This additional part. Does it make the, overall optimization much slower to have this green part or not? Okay. So the green part itself, just evaluating the residuals, seems very fast to me because you have this automatic differentiation. So in TensorFlow, for example, it just provides the terms like, it's some kind of forward pass. For example, let's say you want space derivative of t in the y direction, you get it right away. So computing the green is super fast, okay? But your question is actually, because you have this green contribution, you're kind of changing the landscape of the loss function, because the loss function now is not exactly the same along the parameter direction, right? So you're trying to optimize for the parameter theta to minimize, you're trying to optimize the parameter to minimize the loss. But the shape of the loss is changing because you have this new green contribution. So your question is probably, does it make the optimization slower? Right?
Yeah, so the reason why I was wondering this is because if I see behind that PDE like an operational software, like for weather forecasting or for ocean forecasting, then they are like computationally very expensive. So I was wondering how much this
No, but
approach...
that's the thing, Rosella. Actually, this green part is evaluating, for example, those equations, right? So to evaluate, let's say, the first term, you need gradient of t as a function of time, right? Okay. But you don't rely on the true solver to evaluate that. You don't call the true solver, you don't call the expensive solver at no time. What you do is you get the derivative of temperature with respect to time from the network. Because the network is, it's complex because you have all these connections and all these neurons. But if you zoom on a particular neuron, the equation you have inside is very simple. It's just the activation function is, for example, some hyperbolic tangent or something. So taking derivatives with chain rules, taking derivatives of the outputs with respect to the inputs is like super fast.
Because so you don't run the PDE, let's say.
No, you run the PDE. You run the PDE to collect the data going into the label term.
Okay. Now it makes sense. So now I understand why you say it's fast.
Yes.
Okay.
Yeah, sorry. This is
yeah, because actually you use something already let's say computed.
Yeah, that's the paradox a little bit. I'm computing this, I'm saving data in a few positions, okay?
Okay.
And I'm going to use that in the blue term, and then the green one is only coming from the network.
Okay, I see. Okay, now it's clear. Thank you.
Because if I was using it from the real solver, then the residual will be 0, because hopefully your real solver solves the equations properly.
Yeah, but it's the machine learning that doesn't predict the right solution.
Yeah, exactly. So at the beginning, when the network is not very well calibrated, when you evaluate those residuals, they are not 0, because they are basically the right-hand side. They are the reminders of the PDEs, but computed on the network.
Okay, it's clear now. Thank you.
Yes.
Thank you. I see there's a question of Nassim. So Nassim, would you please unmute yourself?
Yes, hi. Can you hear me?
Yes.
Yeah, perfect. So I have a question regarding the way you enforce the PDE. So in most of the presentation I have seen with the PIN, the PDE is enforced strongly. And so therefore it's clear to me how you use automatic differentiation of TensorFlow to compute the residual. But I think in your slide you mentioned weakly enforces PDE. So do you mean like that you consider the weak form? And if yes, so how do you use the TensorFlow automatic differentiation? How that can be helpful to you to compute the weak form of the PDE? It's not clear to me how you handle the constraint.
No, when I say weakly, maybe maybe that was not the right term to use. What I mean is that you evaluate, for example, the residual of equation 1. Okay, that's going to be one number. Okay, so at one particular point, the residual is just a single number. Okay, and then I have my next equation. So I have 3 equations for the momentum, right? So it's like 3 numbers. And then I have the divergence. It's like I have 5 members, okay? And all these contribution, those 5 members at all these points that I was representing with those stars, they are summed all together, okay? And in the end of the day, at the end of the day, all those terms are just going to provide a single value for the loss function, right?
Yes.
So when I say weak, I mean it's imposed in some kind of soft manner. Everything is lumped together and you're trying to minimize the loss function. But because you have so many things in the loss function, for example, you're not guaranteed that the divergence is going to be exactly 0. You cram everything together in a single number and you're trying to minimize that. It is different if, for example, you enforce a boundary conditions, you know, for example, velocity is 0 exactly at the wall, and maybe you build a network that satisfies this exactly. Those are other approaches. So when I meant weakly, I didn't mean a weak form. I meant it's a soft constraint. It's not strongly enforced. For example, you know, when you consider a system of equations like this is actually incomplete, right? I will need to specify some boundary conditions. So I have a temperature that is imposed at the bottom, temperature at the top. I have velocity 0 at the walls. So I have plenty of boundary conditions that I need to enforce in a certain way, right?
Okay, thank you. Yeah, it's clear. And so another question. So have you noticed any drawbacks in using the PD in the strong form rather than having a weak form, as it is the case for like when you solve the PD directly with the PD solver? Have you noticed any downsides?
It's you know, it's in a sense it's very flexible because of this automatic differentiation. You can, or maybe if you have some symmetry that you know, if you have some invariants, you can add them into the term. So it's very convenient. You know, you put everything you want into this loss, but at the end of the day, you need to minimize this quantity. And if you keep adding things, probably it creates, you know, a very complex shape with a lot of local minima. And then it's a matter of actually minimizing this quantity, and it could become difficult, or maybe you have some equations that are more difficult actually to minimize that other ones. So it's hard to say, you know, it's hard to say, to compare really. It's kind of a completely new approach. You have no mesh, right? I have no mesh in space, no mesh in time. So it's a different paradigm. It's difficult to conclude really which one is better than the other one.
Okay, great. Thank you for your answer.
Sure.
Actually, I think we may have time for one last very short question, if that's possible. So I see the hands of Cesar. So Cesar, would you please unmute yourself?
Yeah, thank you, Didier, for the talk. Very quickly, in terms of like vanishing and exploding gradients, do you have to deal with a lot of those problems or challenges when training this network?
You have this kind of behavior at the beginning where it's oscillating a lot, you see, but then eventually it's kind of okay. I mean, but it's difficult to answer because I've been doing, you see, you have different cycles, and within the different cycles, I have a different learning rate. So all of this, I had to adjust it a little bit. You know, I've tried to follow some guidelines by Benjo and some people, you know, giving some guidelines on the choice of hyperparameters. You see, I was doing this old case for a simpler application. I put the results here. So this is the error, just changing the mini batch size. So I do everything the same. I just lower the mini batch size from 10,000 to 2,000. So basically I'm picking into my data by smaller amount, and that lowered the error. So I would say that I haven't encountered, very main problems in exploding gradients and things like that. But there is a lot of works done on actually trying to adaptively weight actually the different terms as you progress into the minimization. So normally PINS has a lot of trouble with problems with, how do you say, changing dynamics, for example, where you have large scales, small scales. So there is a lot of people actually showing that sometimes PIN doesn't work. But in my case, I don't know if I was lucky, but it was working pretty nicely for, especially for 3D turbulent flows. I was quite surprised to get nice results, because most of the things in Navier-Stokes, you have very small applications, and here it's even more difficult because you have this advection of this temperature field that is going to retroact on the Navier-Stokes. So it's more coupled and more challenging in a way than just Navier-Stokes, I guess.
Thank you for the clarification.
Yes.
So thank you, Didier. Thank you again for the presentation. And
sure.
Yeah, thank you everyone for attending this meeting. So have a nice evening to all of you.
Yeah, thank you. Thank you to you guys.
Thank you. Bye.
If you have
Bye.
questions, you can email me. Okay, bye-bye. See you.